Okay, so welcome everyone to the seminar series. This is the seminars as a part of the Responsible AI program. Responsible AI is a multidisciplinary, multi-sector training initiative to build sustainable connections, research training, knowledge capacity building, and a pipeline of highly qualified trainees in Canada's fastest growing knowledge economy sector, that is AI. The Responsible AI initiative is a part of the NSERC Create, which is NSERC Collaborative Research and Training Experience program. Today, we are very honored to welcome Dr. Freddy Lecue. Dr. Freddy Lecue is the Chief Artificial Intelligence Scientist at Cortex Center for Research and Technology in Artificial Intelligence Expertise at Thales in Montreal. He's also a research associate at INRIA in Weimix, Sofia, Antipolis, France. Before joining the R&D lab at Thales, he was AI R&D lead at Accenture Lab in Ireland from 2016 to 2018. Prior to that, he was a research scientist, lead investigator in large-scale reasoning systems at IBM Research from 2011 to 2016, a research fellow at the University of Manchester from 2008 to 2011, and a research engineer at Orange Labs from 2005 to 2008. His research area is at the frontier of intelligence, learning, reasoning systems, and Internet of Things. He has a strong interest in explainable AI, that is AI systems, models, and results which can be explained to humans and business experts. So thank you very much for accepting our invitation. We are very pleased to have you, and the floor is yours. Please take it away.
Thank you. Thank you so much for the introduction. Thank you so much for the invitation. So I'm very pleased to be with you today to start a series on of the presentations on the topic of explainable AI. So I'm expecting this presentation to be 50 minutes, and then we can have time for discussing concepts or questions that you have in the field. So I'm very we'll be more than happy to have long discussions after that, because I think now the virtual conferences and events make that informal discussions kind of disappear. So if you want to stay around and we have kind of informal chat after that, I'm more happy to do it. So I'm as mentioned. So I'm part of Thales. So it's a company that basically build hardware and software and system for vehicles operating up in the air, under the oceans. So we design, we build, and we integrate AI systems in satellites, in trains, in planes, submarines, for many different purposes, but mainly for navigation, but also for situational awareness, for detecting obstacles, for detecting anomalies. So, and when you think about those kind of vehicles, so it's really go beyond cars. There are really vehicles that are equipped with many kind of data. So with many kind of sensors that sense data. And sensors might be LiDARs, radars, sonars, optical cameras. They're very kind of very broad. So they're broad, and they work right, and they use more and more machine learning models. Not only, I mean, we do planning, and we do representation and reasoning, we do search, but then when we thinking about pushing AI systems in this environment, you have the questions about trust and certifications, regulations, because that you're pushing those in systems that will be operating with for humans and with humans. So that's always a question about how you can handle those situations. So that's why the company I'm working for is strongly, and there's a strongly need for explanation, certification, regulation. And then, basically any model that we build on top of data, a large amount of data, that requires some kind of explanations. And explanation is a broad term, it's pretty large. It means many different things for many different people. So I'll try to define what is it and what it means for us. but there are many terms. So you may have heard interpretation, you may have heard justifications, diagnosis, root cause analysis. It's kind of the same lexical family of terms that means kind of the same thing depending on who is using it and depending on which where are you coming from. You may have a different angle and different dimensions, but it's pretty broad. So so what I'm going to describe is trying to give you a bit of motivation first, then giving you an overview that explainability in AI is not only for machine learning and not only for deep neural network. So but that also required for much more than that. And it's only, I mean, the work we're seeing now on explainable AI for deep neural network is only the surface of all the activities going on. So, and if you're interested in the field, don't get trapped in the spirit of always building a neural network, forgetting interpretation. You can use much simpler model for that, and I also describe some of it. So in terms of scope, so explainable AI is one of the pillars of what's trustable AI. So it's basically environment when you build systems that use some kind of AI, and AI can be broadly defined as a scheduler, planner, robots. So it's very broad, right? It's beyond machine learning. It's very intelligent systems that make use of any kind of knowledge derived from data or from experts, but and trust is very important. And to get the trust from humans, and especially in the industry I am, in defense and government initiatives, but not only, also in financial context, people require, they do have regulation. So then when the human is saying, okay, let's use that model and push it in the software for making decisions, they need to be trustable. So they need to you need to have gatekeepers. And those gatekeepers, they are basically engineering tools or engineering tricks or engineering gatekeeper for making sure that whatever the system is doing in a trustable way. And there's one way to ensuring that. There is the explainable AI part, which is explain the rationale of a decision or explaining the rationale of a model. So for algorithmic, it's easy because in algorithmic sense, it's a list of instructions, and you can make the validations with unit tests and edge cases. So, and you can make sure that it does have the right behavior. Then when you go towards much more machine learning, which is basically using an algorithm for deriving a model on top of data, well, there are edge cases that you won't be able to see or you haven't seen, and then you end up in issues related to sometimes bias and discrimination. So then how you cover it, and that's kind of the responsible AI dimension, which try to address the chart of what's the AI vision for a company, and what do they define as responsible, and what do they want really to implement. And then of course you have the two remaining ones, which are the valid AI. So whatever that you do, it needs to be conform to a solutions or to requirements that you have. So if you build a model that aim at predicting if you're getting a loan and getting the loan granted, you should not deviate and should not do something else. Need to be in the scope, and also valid in terms of resolution, not deviate from what the human should have been doing, or if it's doing it, then having some kind of rationale why we have such a behavior. Maybe the data is not so much aligned with the mission. And then, so you have the privacy preserving part, which is very important as data is getting much more, user or customer data is getting much more protected by different regulations. You may have heard of the GDPR in Europe. And you have similar regulations coming in place or in discussions in the US with the California Act on the subject and others. So it's getting really much more attention. And if you ending building this trustability. That's the kind of the pillars. They are not the main ones, but they are the main ones, but there are others that gravitate around those. So part one, introduction and motivation. So as I'm coming from industry, I'm kind of biased towards what the clients I'm working with, or the different stakeholders, what do they need. So I'll position usually that view against the GAFAM point of view in terms of large amount of data use, and so well, you'll see where I'm coming from, but just to show the different angle and kind of while dealing with different problems and challenges. So just to give you some motivations. So from a business perspective, if you look at the tech companies, they have access to all of the data that we have and that we generate. So for cookies and interaction with systems, or buying products, they have all of these information interactions, maybe through social media and many others. And so then they can use that information and start making recommendations, tagging friends. So there are examples of things that they can be doing, and they're really pretty good and it's pretty useful. And it's done and pretty nicely because of the scale at the scale they're operating. They have so much data that building model that can be generalized is definitely working. The thing is, as they work in a much more giving free advice, as we are kind of the product in that space, as we do provide the data. Whatever recommendation that we get as the user, we can use the recommendation and maybe watch the next movie, or buy the next product, or being biased by those recommendations. But at the end, even if it does have some kind of impact on things that we interact with or that we buy, doesn't really have a catastrophic impact on our life. If we're watching or buying the wrong next product because of the algorithm or the model did the wrong thing, it's not really the end of the world. So that means I'll getting an explanation on why I get such a movie. It might be useful. And we've seen such implementations from Meta, where they, in the Facebook applications, they explain why you get, or they provide information on why you get a particular news feeds, and it's because you're connected to few people that watch it, and you're interested in the few topics, so they can trace back and give you this information. But it's not really, I mean, that's something we can use, but do we as a user, do we actions, or will we actions on top of that information? Well, not so sure, right? They can improve, obviously, the models that they have been built, but from an explanation perspective, it's not really a must to have. And you see, and you when you listen to the AI top experts from those companies, they say it's a nice to have, but it's not really a must, right? It's not really, they care much more about the scalability and having the right level of accuracy. And but the industry I'm coming from, they are dealing with critical systems. So that means first, we don't operate with large amount of data. So here you have examples of operators trying to get mines from World War, and they try to retract or remove it from the very deep sea, and that's a very challenging task, because it's a computer vision task. That's not only a computer vision, because we use sonars, and there's a few interpretation, use spectrogram and so on, but it's kind of a computer vision task. But at the end, when they make a decisions to spend some time getting access to it, removing it, or just looking at it and say that's not one and let's move on, it may have a huge impact. You may have a boat going through next and then getting impacted by that mine, and that could have huge dramatic impact. And that's why when those people that you see here, when they do operate, the first thing they would add, they say, okay, accuracy, we definitely need that, but we also need kind of bulletproof for us to validate the decisions that the system has been made. So what's the explanation? Why do we have such a behavior? Why we do have such recommendations? Is there any outcome I can use for me to trigger other double check or triple check, so then they can make the right decisions? And that's because usually those people, they don't operate in a one-shot process. It's not like they see something, that's it and that's done, or they see elements and then they take further angles, and then they, depending on what information they may have seen shadow on the shape, so then they turn around, they take different angles, and then they may take some sample around just to get a feeling of what's the environment like. So it's kind of a very complex and environment, and when they make these decisions, they want system that is interactive. They want system that provides explanation, but not in a one shot. So I don't know if you're familiar with the field of explainable machine learning, especially latency maps, something we will cover later. But having super pixel views of what that's a mine doesn't really help them. Usually the operators, they have the same, usually latency maps doesn't really work so well, and they need more. So they need kind of much more descriptive information. So 3D rendering of what we may have this information. So they really look really beyond what's the only one-shot explanation that the community is providing. The same if you're moving to trains. So we do have a project on autonomous trains, working with our colleagues in Toronto on the project, and one of the challenges, again, building a model is one thing, detecting obstacles using this model is another one, and but getting embedded in a train that take a fully automatic decision there's a huge gap. So you won't reach that gap in a few years. You usually have the human in the loop, and still, even if you have the human in the loop, usually the model need to be safeguarded by many different engineering trick or any engineering gatekeepers. So then the model is only operating when it should be operating. So, and then when you go on edge cases, then you do have other much more classic rule-based systems. And that's why trains and transportations in general, they are highly regulated, and they usually say, okay, that's the algorithm, that's the way it's working. Here are the edge cases. If you want to be certified, this is what you need to fill in. But then when you say, oh, I do have a model, and it does work with accuracy and with some particular accuracy points, people might get confused. Say, well, that's not how regulation transportation is working. Usually, when we work with them, they always mention one out of a million errors. And when we do object detections, I mean, we much more in the 10%-ish percentage error, right? So there's a huge gap, and again, you need to take this with attention, but that's something which is very important. And but it's not only critical systems. I mean, it's true for I mean, particularly, I mean, here examples are example of bias and discriminations, and usually, well, explanation is coming here to provide a rationale of what a model is doing and why we get the results. But usually, if the explanation might be useful for understanding what's wrong with my data actually. So the model might be wrong, but the model, of course, if it's trained and if it's not nicely and well engineered, you can question the model and the algorithm used for building the model. But if you do have a robust enough or kind of a well-engineered model, and it doesn't perform well, and you can get explanation which doesn't make sense, that probably means that the data is maybe off. And you see many examples. I mean, there's very nice work on the disparity or in conventional gender classification that show that there is some gender and some ethnicity group that were underrepresented, and you have a huge gap. So that's something that you can learn. And you have also the recent example from Zoom where you have this blurring functionality, and for some reasons, some people, again, with some ethnicities, they just get their body removed, or so that caused challenges, and then you may start asking the questions, well, the model might be wrong, but the data underlying it's also questionable. So you go much more beyond critical systems. You go towards a system that touch people and ethics and more than that. So I think it's very all nicely connected. Okay, so move to next slide. So that gives you a sense that it's pretty broad, and it's touching many different areas. And I mentioned it quickly, but you go to finance, it's definitely a must. Healthcare, medical domains, they are where explainability is required. So if you look at from an AI as a black box perspective, if you take the model, and again here, well, I'm schematizing using a network, but it could be any complex models with non-linearity. And then if you don't really convince the persons, again, think about the critical situations. They may say, okay, nice, I see very nice metrics. The people might not be expert, but again, you have plenty of metrics you can use for evaluating models, but then they may say, okay, but why do I get that? And usually people thinking along those lines. I would also agree that depending on the profile of person, if you're scientists and engineers or a domain expert, there's a kind of level of abstractions you can make to get an understanding, but you still always need kind of a lines between the different stakeholders to convey whatever decision it is. So then, depending on who is operating, you may have business owners that may ask, why can I trust the AI decision? How do I answer these customer complaints? How do I monitor, debug this model? I can make this model better. So can I make some optimizations? Are those decisions fair? So usually people have more questions. And I think even if though this talk it's much more on explainability, I think it shows that the interaction human system is more than only a one shot. It's a human is interacting with the systems, is getting some accuracy, and then he's starting questioning and asking and double checking and triple checking and so forth. So they only try to get a sense of, well, am I sure that in the perimeter I'm responsible? Does it making the right decision? So that's something that we need to be considered. And in terms of evaluation, I think it's important. And so now you see much more and more evaluation metrics for quantifying and qualifying explainability. So you see many metrics. I mean, there's this notion of deletion metrics, insertion metrics, the mu fidelity metrics. They are example of metrics. So we start seeing emerging metrics for that. But there are many ways you can measure it, and depending on who you're operating with, they might need different elements for evaluating that the explainability is good. And again, how you define good is an open question, depending on who you operate with. It might be, maybe you want something short, or maybe you want all the explanation, and that's exactly what is defined under the lines of succinctness or completeness. You may want something, whatever the size, but something you can easily catch and that resonates with you, and that's something comprehensible. And comprehensibility is interesting because it's something that an element or an explanation for decisions, or an explanation for any rational or irrational decision, can be provided for a human, but depending on who getting that result, you may get it or not, right? Depending on the context. So you might use some terms which is very too technical and you have no understanding and no comprehensibility. But someone with high and deep expertise, if you explain that a model is making such a loan approval decision because, and then it's starting playing with rates and credit history, and if you don't have these notions of these concepts, you say, okay, what does that mean? But the persons living or understanding those concepts will grasp exactly what does that mean. So comprehensibility is really about only customization of the explanation. And then, I mean, explanation is something you provide to a system to build on top. Usually, it's not like I'm giving you an explanation. If you ask me a clarifications and I explain, when you use it for making your judgments, so it's used for a next step. It's not the end of the conversation. You use it for actioning it. So then the clarification helps you saying, well, I'm not agree or disagree, and if I'm a disagree, there's further actions. But those explanations should be used for what we call actionability. So you use for actioning. Maybe you want your model to be better. So if I can explain why the data or why the model is performing very badly, then I can use it to add much more heterogeneity in the data or add much more diversity. Or maybe I want to prevent such a behavior, so I need to deal with some particular population. So I won't touch that population because it's not designed for it. So then you can better repurpose your model. So that's on actionability, and I think that's very important. Okay, so now I'll go on deep neural network. But before that, I want to show that picture about AI in general. So I haven't invented the different field that you see here. That's usually if you go and submit to a general AI conference like AAAI or ISHCAI, you'll be asked to get your papers submitted in one of those buckets. And the same if you go to the conference, which actually is happening this week, you will see usually, well, groups of papers, and they group for per topics. Well, they might subspecializing it because it is still broad topic, but it's kind of where they break down the field of AI. So you have planning, search, and UAI, which is under uncertainty in AI. You have knowledge representation and reasoning for KR, and you have all of those different fields. And what I want to cover with this slide is, even if we have plenty of those fields, well, you also have plenty of techniques of explanations that try to solve explanations in the particular field. So obviously machine learning, dependency plot, feature importance, surrogate models. I mean, they've been here for years before the 2000s, where you get stronger interest in the field. It's there. It has been there for years, coming up and saying, try to see, is there any wrong correlations? Can I capture the most important features so then I can collect more, or maybe cleanse at least those features from the data? So that's been there for years to help. In planning, I mean, it's very well known that understanding how you reach a conclusions given your initial states and the set of actions that you have. Explanation is the set of actions that you take, and which constraint that you take. Each actions may have a weight, and they may have they may have effects and preconditions. And I mean, what's the rationale of getting this particular plan? So I want to have this robot moving from A to B, and there are many actions, it's kind of a maze, and they want to go. There are many constraints. So why did you end up in taking this? And there are questions. So planning, robotics, knowledge representation, and reasoning, the usual suspect when you think about explanation, because that's been studied well, for years. They have very dedicated terms for that. So abductions, diagnostic, finding the right root cause. There are examples of inherent reasoning mechanism for that. So if you're interested in those particular elements, that's where you could find tools for providing explanations. But again, you will need some kind of logical representations. And then I'm not describing all, but you do have a concern about explanations in all of those different fields. So that's something that people have been studied for years. In search, you can find a tutorial on eXplainable. I don't remember the exact title, but there were explainability in the title of the tutorial, and it was 15 years ago. So that's not a new topic. There's plenty of concept and principle we can reuse and we can apply, and maybe the problem that you have might be able to be solved by the pure optimization task and the satisfying constraints in a scheduling domain, and they have tools for explainability already. There's been a strong interest. It's just that now that deep neural net is exposing strong and great level of accuracy for solving image classifications or language generations. Now that they have this kind of right level of ability, there is this question on how you can provide explanations, but there's a lot of inspiration that could be used. So that's something I wanted to convey, is that explainability is much more than deep neural network and machine learning. So, but next I'll go a bit much more deep neural net, because that's where people nowadays spend more of the day of the times. And if you look at the NeurIPS 2021 papers on explainability and interpretability, lots of the work were on language model, on reinforcement learning, autoencoders, so and clustering and supervised machine learning. So they were all in this. So obviously, well, that's a conference dedicated to the field, but that gives a sense of what was the scope. Okay. So yeah, so now what I want to show is well, explainability, and that's a presentation which aimed at being a bit to provide a bit of kind of visibility of what's good, what's bad, and what's not that well, what we think, what might be not the great way of capturing explanations, and because you have many tools, and there's a kind of strong effort in many different dimensions. So want to show that in some application, I've been talked to many different clients and customers, and they don't see this as a way for help to provide explanation. It does help some particular client segments or market segment. So just to provide a bit of criticism on all what has been done. Okay, so what I'm describing as the good is something I touch a bit in the introduction. It's really the multi-step or the interactive dimension. Is that an explanation is not a one-shot. It's not a one-shot. It's first it's multimodal. So you may get data coming from many sources. So as a user, if you do have a system that make a decision, I take the example of maybe of a car. They will have at least two medium to interpret and to make decisions. They'll have the lidars and they have optical cameras. If you go to trains, they also have radars. So they use different signals, and you can build an end-to-end architecture and combine all of them, or you can use a combination. So there are different ways of doing it. So you have different architectures, but it's getting much more multimodal. And as we moving on, we can imagine taking or sound information. So you can have system that can hear and now capture the signals from pulsions and others. So you can expand and stack on top. And then in the context of cars, then you may imagine that why did you strike here? And maybe I could not see anything, but actually maybe something from the top is coming up, or not coming up, but something that you can hear, a person crying later on, further on, and maybe that's information that the car should stop because of whatever things that the machines cannot see. So imagine that now that you do have a lot of those medium, and then how you combine the two, or the three or the four. So in this example here that you see on the picture, it's a very simple example of predicting while you do classification of an image, and you try to predict that's a fish. Usually one-shot explainer, they just say, I predict that's a fish. And best case scenario, they do saliency maps on top. Well, they may have many different techniques. And but we could imagine now that we can have the user interacting with it and providing feedback, so then they can say, okay, but why is that so? And then the system is providing and is getting challenged, and it's trying to find a way and saying, okay, this is what I get in terms of the super pixels, and that gives you idea of which chunk of the picture is driving towards the right class and which one is not. And then the user can keep challenging and say, yeah, show me some examples, or it could even be more abstract, asking, okay, yeah, but why do you believe? Do you have more evidence? And then they can give examples. Say, okay, well, in the model, I see very similar pictures, and they were fishes, so probably this is one. And then you can have the user keep asking questions. And I really think explanation is going towards having system doing interactions and combining existing techniques. So here it's combination of science maps and example-based explanations. You could use concept-based explanations, would extract parts, maybe part of the picture, say, okay, that's the tail of a fish, that's the head of the fish, and then that provide much more information about what's the segmentation like and what the concept of those segments. So you could go even further, and then the user could ask, yeah, but it sounds like the tail is much bigger than usual, and the system could say, well, and here is the information about tail I have, and here it's example of fish with long tails. So, and then you can think about system that try to convince the users, but not only saying, okay, that's the pixel, here you are, here you go, that's it, right? So, so the good, it's you have the human in the loop. It's iterative. It's based on the operators. Here we don't target the developer. It's really who is using the app or who is using the system. And domain knowledge is required because you may expect the user to ask very niche and detailed questions, and that's probably where you might need knowledge. So so yeah, so that's kind of the good. I think there are good examples and good directions. I mean, based on what I've seen in the industry. The not so bad, and you will see my discourse is really going towards, I think the more semantics you get, the better. So, and it's so earlier I mentioned concept and representations and part of the pictures, and that's kind of where you start labeling informations, but much more rich information. And here is the same. It's some work started from MIT on the work on network dissections and moved to compositional explanations, where they really try to label neurons. So initially, the guys from MIT a few years back, 5 years back, they try to put a label on a neuron. So they work on the segmentation data task, and they try to label based on activation. So they compute intersections over unions as an interpretation method, but they try to put a label. And then those guys from MIT and Stanford a year ago, now they say, okay, yeah, but what if we could if we could maybe provide the compositional explanations? And the rationale was not to make it more complex. It was to increase the overall score. So in the initial work 5 years ago, David Bo and his team, they assigned a score of a label to be representative for a neuron, and they score it, and they call these scores the interpretation score, and it's usually around 0.2 scores. So that means a 0.2 scores of these neurons to be responsible for airplanes, for instance. Or here in the example, it's a 0.2 for water descriptors. And those guys, they say, okay, let's try to push the boundaries further. So then we try to move this 20%. So actually it was more in the 15-ish, and the guys from MIT and Stanford, they push it to much more, 20-ish%. So, and then they say, okay, let's make the neuron a bit more expressive, so at least they can capture more concepts. And then they much more kind of, they have a better interpretation. So when we have a neurons, okay, sure, you have a longer list of concepts, but you're much more inclusive. You're much more inclusive. And what you see here is, you see that based on the different neurons, a neuron. So here, for example, the 483 on the left-hand side, they compute, give a score, and the description was, it's water or river and not blue. And what's interesting, it's the description they end up with. So, and the score was pretty high. And you see where I'm coming from now. You see that, oh, now that we have description, what I can do with it. Well, first you can say, okay, which neuron are activated, and what's a deep description of my picture? What's the explanation? And that's because, oh, your image is water and river, and that's not blue. And you can even think about composing neurons, and which, and because here we're only targeting a layer, right? So you can think about further layers and doing fancy things. And then you can start manipulating it and say, okay, let's say now I take the picture, and whether than having the water not blue, I'll put it in blue. Does this neuron really capture the not blue or the color blue? It turned out that it's right. So if you change the color, then you do the inference, you see on the 4 neural network, you get a different description. So it was a swimming hole, and now it's a grotto. So the prediction had changed. So that means they really find some kind of connections at the neuron level to manipulate the picture. So before that, you have only the neural network. You have no idea how you can make manipulation of the image, or what kind of image you need to use to improve your training. So here you may ask the question, but why do you on earth need to manipulate data? Well, actually, you can use it for making your model better or more robust, much more much better in handling bias or discrimination, by saying, okay, for moving from blue to green, I want to have the same classification results. So then that means I need to further train on that data, or I need this neuron now to learn that new concept. So maybe I need to change, and you can start tuning and the neural network in that sense, or retraining for some purpose. And that really gives some kind of very niche tools for manipulating neural network. Okay, so I'll move a bit faster because we're already 50 minutes. I haven't seen the time moving so much. So okay, so the bad now. So the bad, well, again, depend on the use that you make, but there is some work that make visualization of what the neuron is. So here it's kind of the same work as the one I showed before, but it's only purely visual, and what it's doing, it's mainly taking inputs and trying to have a visualization of what the neuron is basically seeing. And then from a human perspective, you can see, for instance, there are a few examples. If you use the CLIP architecture, which is behind DALI from OpenAI, you can see that the unit 118 for layer 4, they compute pumpkin-like pictures. I think it's good, but it's remaining at the visualization perspective. And sometimes it's even better to look at the examples and say, okay, what are the examples or strongly activated? And here you really see pumpkins. And then you can, in the same way people from MIT has been doing, you can start labeling units. And I mentioned as the bad, I mean, it's not that bad, it just, there's no really human interaction. It's mainly based on the activation on the neuron, and it's based on the content, but you don't have any semantics. So there's no representation that you can use for interpretations. And the validation is mainly qualitative, so there's no quantitative measure, and you're mainly aiming at the developer here. So, and as you see in the list, when I mentioned bad, it's not just it's a bad stamp. It just in terms of who is validating, who is using it, how they interact with it. That's really in that spirit. And knowledge, it's implicitly. Maybe, well, you can add some, you can build on top, but it's purely implicit. And then the ugly one, and again, think about interaction, construction, validations, and knowledge. You have all of those work on silency map related techniques. I think you have few more every year where they slightly change the gradient backpropagations mechanisms up to the pixels, and they slightly change a few things. Now I've seen some one where they even combine them, and they show that it's not only one technique you need to use, but it's more than one. And they show that it's actually even, truly better. So don't use only gradient, use a combination of gradient and pattern attributions and others, and it's even better. But the problem is, at the end, you get super pixels and human interactions. How you do interact? You get super pixels, okay, but what's next? I mean, you color the pixels and tell me that's the most important. Well, first, that's not true all the case. Sometimes you cannot say that's right. If you cherry picked, you definitely see it. If you don't, you may have challenges in finding that's the convincing explanation. And that's from a human perspective, that's maybe kind of challenging. And then the construction, it's purely gradient based, so there's no semantic involved. There's no such a notion. And I think if you want to provide good developer interpretations, you'll need to get better. You need to get better or much more explicit representation of information. And validation is mainly qualitative. I mentioned now there's a few quantitative metrics. The new fidelity is an example, but it's still lacking much more quantitative. And if you really want to be convinced, you will be convinced by cherry-picked examples. You have some on average that do work, but then moving slightly the task that you're doing, and you may have challenges. And knowledge, there's no really knowledge. It's only you purely working on the data and input that you get. And I think there's much more that we can leverage on. And that's where then I say, okay, well, based on these facts on what's good and what's bad, then how you can boost neural network interpretation with graph. So how does it work so I just want to show a kind of a easy way to solve the problem, or try to solve the problem, and how you will do it based on existing state-of-the-art technique. So you have a boulder on the train, and you want to detect it, and you want to get the explanation of why this is an obstacle. And well, as a human, it's obscuring the trains, and you should definitely stop here, right? Otherwise, you might be in trouble. But if you use VGG16 on top, you don't do any fancy fine-tuning, you just keep it as it is. So there's nothing new. You get this classification, this subject detected. You get this one detected. Actually, you have at least, I think in this picture, there's 20-ish number of objects detected, but here's the one with the highest score. And actually, those ones were also detected, but the threshold were much lower. So you may ask, yeah, but that's mean, they are here, but the scores are not right. So first, if you ask a system to operate here and to say, what shall I be doing? I mean, the obstacle will be missed, and the lumber mill won't be any of help here. So you just crashed, right? Well, obviously you have a human in the loop, so you won't. But if you want, the system won't be of any use here. So if you use explanation, you do explanation on the wrong objects. You can use many different techniques. This is what you get, and this is no use, as I mentioned. And if you look at the explanations, if you just look back, the lumber mill, what is it? So it's a sawmill or lumber mills. So a facility where you have logs. Okay, it does make sense. And you may say, yeah, but what's missing here? So I wanted to have the boulder detected and get an explanation why is it an obstacle, and I get the log here. So you may ask what's missing, and simply what's missing, it's all the context, and all the context is all information that you have and that should be combined together. But there's no chance that the neural network gonna make any sense out of the external, well, out of the context you get. You get those objects, but he has no meaning that railway and boulders might be linked. There is no connections between tunnel, between speed of a train and impact on a boulder. There's no such a thing. All of those things, however, you can find it in text representations in DBpedia. If you look at DBpedia on train accidents, on boulders, and rail transport, you get that information. So that means you don't need to hard code this information. That's there. And if it's there, if those terms, boulders, railway, and trains, if they all connected by whatever co-occurrence mechanisms, even very simple one, then you can maybe use it for boosting your object detections mechanisms in a particular context. Of course, you may have trouble if you try to generalize it, because a boulder, boulder in transport and maybe boulder and climbing there's something that you operate, and they have difference. So you need to be careful. But actually, what you want the system to learn, to say, okay, I can capture detected objects. I'm not so sure about the confidence, but the context could help me in boosting that confidence. Of course, people from machine learning community will say, just fine tune it, and that works. That's true. But what if you change situations and situations? Do you still need to fine tune it for a particular situation? I mean, that's kind of costly, and that's not that easy to do. So let's use as it is and just say, let's try to boost those scores by identifying any co-occurrence of terms in DBpedia, or which is, by the way, the DB version of Wikipedia. And then you can boost those scores. And railway, you can boost it from 11% to 90, and boulders from 9 to 81. So that's a pretty good boost. So, and you may have and then the descriptions of the explanation. So here really the thing is to say, the idea I want to convey is, you can use the neural network and the model behind for doing your task, but think about the object detected. Even if they have wrong or bad accuracy, can you try to reconnect all of those things that the network detected, and maybe prioritizing the scores based on how they occur in some documents? Obviously, documents which is relevant, you won't connect this with a book on trains, right? You may get completely lose the connection between boulders and train and accident, and then you make the right connections, and that's a way to go. So that's something we did, and we work with the train authority in Toronto, and to work on this autonomous train concept. So we published it, we patented it, and it's under use by our colleagues. So I moved to another topic. So just checking time. Okay, there's a bit of time. So on some of the latest work that we work on interpreting visual question answering results with graph. So what's visual question answering? You have an image, you want to ask a textual questions and you want to get the answers. That's visual question answering. So it's basically answering textual questions on a visual content. And usually the task is a classification task where you have all the set of answers predefined, and you need to figure out which answers goes to that question. So and then you usually in those contexts you have you have different backbones. So you have the computer vision backbone and the text backbone. Yeah, so that's, you have the CNN part and the ONN part. You join the embeddings, and that's a classification. So that's that's work that addressing visual question answering. And you see over time the different models and the different scores that they get. They get pretty high, up to a certain range, but they have limitations. Answers, they are required to be in the images. Of course, they need to be in the final classification head, so all the different results, but the answers need to be in the image. So there is no chance. So you need to ask. So an example of a picture where the answer is not an image. If I say in which year in which year the founder of this drink has been founded, and you see someone drinking a Coca-Cola can, and the year is not there, right? So, well, and then how you get information. So there's very limited work on that, and knowledge is limited. So because the knowledge of having this year is limited. So therefore some questions cannot be correctly answered anyway, as some level of basic reasoning is required here. You need some level of basic reasoning to say, okay, that's a person that's drinking a can. The can, it's Coca-Cola can, and that is a brand, and the brand is funded by a person, and that person is born in a particular location, and it's funded in a particular year. So there's kind of a long chain kind of reasoning if we follow a graph. And state of the art in visual question answering, they say, yeah, okay, let's do it, and they basically do a huge search, and they post it with plenty of different. So they do an external search, and they basically build an index on top of pictures, images, and descriptions of the pictures. You can do it, but the reasoning will be limited. You can use graph embedding based techniques. So that's another one, and graph fusion based techniques. So that's one of the work that we publish at TMNLP, that we try to use a knowledge graph on top. So, but what we try to do, and here you see the results compared to the previous one. The results are pretty low. So the 59%, well, 60%-ish max for the highest accuracy result on those tasks. So it's a very challenging task. But they also have limitation, and they don't provide the explanation. So and where we came from, it's say, okay, so there's image, there's text, and there's this connection between the text of the questions, or the token of the questions, and the images. But how you can make the connection between the two. So we end up with a work that use attention mechanism to connect the two. But then the next question was, well, can you provide explanations on why we get an answer to that questions? And there were no such work. So what we try to do is we try to retrieve explanation, and we use a combination of different tools. And we use knowledge graph, and we try to build explanations that connect the questions here. So you see the questions vertically first, then you have the token captured, or the concept captured in the image. So using the CNN-like architecture, so faster CNN, for instance, and then you have the elements that you get in the concept, in the graph entities. sorry, so that's the question token first. Then that's the concept graph informations. And what we simply try to do, say we get the question, we get the object. Let's add a knowledge graph concept over here, and I try to make the glue between having a relations between the concept we detect and the question, and also connect with the answers. So, and the goal is really to say, okay, there is plenty of token we can retrieve, text token from the questions, well, knowledge graph tokens, and concept tokens from the image object detectors, and try find which elements combine together, and see if that make an explanation. And so we end up with a new architectures that's really combined so we will try facts. So here we simply take the question text, the image, the answers, the potential answers. So you have more than thousands classes. You have your questions, and you try to connect those tokens from the questions and the answers through the concepts that you captured in the image, and basically you have the input and the output, and you try to build well, subgraph that connect all of those, and you try to minimize or maximize the number of concepts used from moving to the input to the output answers. So the answers, we do have it, so we are able to compute the answers, so we know which ones are relevant. So we have the top 10. And then from the inputs, you try to reconnect the input output using concept in the middle. And then you can do it by using fact retrieval module. So that's simply, you look up a knowledge graph. So here we use ConceptNet, and you figure out based on the question. So the question is maybe, let's say, park. So there's a concept park, the token park, and the answers is a skate park. And so what's connecting the two, and then you're looking at ConceptNet and say what's connecting those two, and then you can see, and the idea is really to build that explanation. And what we end up is showing that we get well, pretty good results, up to 39%, and if you use the Oracle case, 54%. I mean, that's that means if you do the right search, you can reach up to 54% accuracy. And then here you have some examples about, you have the image, the questions, and you see how we connect. And for instance, an example of a question, of an answer of an explanation is surfing is an activity in Pacific, and surfboard is related to ocean. So you basically connect the Pacific Ocean, and you relate to, which is the answers to the oceans and the surfers. So you try to make a narrative out of the information. We do have other examples. So I provided the link later on, but you do have other examples. So here show the different examples of things that you can build, and then here are the different results and with high potential. So yeah, and quickly, because I want to make sure we do have time for question. Just very quickly, I have a few slides on well, try to give inspirations on what you can do with labels, graph, and concept. And again, think about not really formal concept, but really something. You look up ConceptNet, it's already pretty good. It's noisy, but you can use to some extent. So then, how you can augment input? So when you do segmentation task, they have labels attached to pixels. So can you use a graph representation of that label rather than only the label? And maybe that will build up some connections and relations. Can you augment, the work I mentioned when you label neurons, rather than having only the label, can you just interface that label with the concept in a graph? And then you can start reasoning about those, the connection between layers and neurons and output and input. There are many potential here. Yeah, that's exactly what I meant here. So then you can use it for augmenting semantics of the labeling part. You can also augment the semantics of the output. So rather than having only a label output, what if you do have class or concept in a much more deeper graph? And then also you can use it for refining descriptions, explanation. So usually captioning is about providing a caption, and everybody get the same. But now if you do have graph and concept with specifications, you can fine tune it to people depending on what they need they might have. You can also, so we have some work that try to explain transfer learning. So when you move from a domain to another domain, you may want to use an existing model. How can you apply it? Is it working? So before doing any testing and fine tuning, we define some way to measure the confidence that transfer learning might be able to work. We also work in the concept-driven domain where the output is changing quite largely. So then how you can explain that the data is changing, and that's especially true for time series. And then more semantic interpretation. You have some work from concept chat, from ACE, from TCAV and CAV. So they have technique that extracts regions or segment and they try to label it. And then if you start labeling it, then you can get a concept-based representation of explanation and start doing interesting things. So here is just giving some kind of thought about where and how you could go about explanations in the field. And I'm concluding it. So so we've seen different parts, the good, the bad, the not so bad, and the ugly parts. So I think the explanation is really a story about how you can combine all of them and how you can take the best of them, and particular context will require a different balance. And I really think it's really a mix, and it's really an interactive way of building explanation, because the human will be consuming it, so they will need to interact with it. And also much more work now going in very deep areas, so let's say silent CMAP or superpixels, and they combine them. And I think it's really now a matter of combining different techniques, maybe a concept, superpixels, you take some of them, and even inside each of them, maybe if you go for example-based, you combine different techniques that will drive examples. And it's and the base is really about the combination of it. And we always say that machine learning is the best way to make your model working is fine-tuning and hyperparameters. And the same for explanation. Explanation will go at how you fine-tune which technique you use and which hyperparameters you, and those hyperparameters will be the scores that you put on top of which technique you use, and you will be using a combination of them. That won't be a one-shot, but will be a combination. So that's really about it for my presentation. So again, thank you for having me here for presenting. And so I'm open to questions or comment or further discussion.
Okay, thank you very much, Freddy. This was very interesting talk. So I'll stop recording here.